So how in the world does a search engine sift through the entire internet in like a fraction of a second? Well, the secret is this idea called MapReduce, and it's actually way simpler than you might think. It's the paradigm that really kicks off the whole big data era and totally changed computing forever. Let's break it down.
To really get why MapReduce was such a game changer, we have to hop in a time machine and go back to the late 90s. Google was facing this absolutely massive challenge. The internet wasn't just big, it was exploding, doubling in size pretty much every year. So they were staring down this crazy question. How on earth do you process and index a digital universe that's growing that fast?
I mean, just look at this growth curve. That's a rocket ship. And we're not just talking about more data. It was a totally different kind of data. It was huge, it was unstructured, all that messy HTML out there, and it was changing all the time. The databases people were using back then, they were built for these single powerful server setups. They would have just melted down. No way could they handle this.
And that brings us right to the heart of the matter. This was a problem of internet scale. The old way of doing things, the old rules of computing, they just didn't work anymore. So the engineers at Google had this huge fork in the road. Do you try to build one gigantic, monstrously powerful, and just absurdly expensive supercomputer to drink from this data fire hose, or do you try something completely different? Could you maybe take thousands and thousands of cheap, regular, off-the-shelf PCs and get them to work together as a team? Their solution was this brilliant 1-2 punch that they laid out in two famous papers. First, in 2003, they tackled the storage problem with something called the Google File System, or GFS. It was a way to reliably store gigantic files across all those cheap machines. Then, in 2004, they dropped the other shoe, MapReduce, which solved the processing problem. So GFS told them what to store, but MapReduce gave them the how to process it. And we're going to focus on the how. So what's the big idea behind this new model? Well, it's a strategy that's as old as time, really, just brilliantly applied to data. Divide and conquer. The core idea is just beautiful in its simplicity. Instead of having one giant machine do all the work, you smash that massive job into tons of tiny, independent little tasks. And then you can run all those little tasks at the same time, in parallel, across your whole army of computers. Now, the best part for a programmer is that you only have to write two really simple functions, map and reduce. The whole framework handles all the messy, complicated stuff in the background, handing out tasks, dealing with computers that fail, and pulling all the results together at the end. All right, so let's get into the nitty-gritty. How do those two functions actually work? First up, the map phase. Okay, think of it this way. Imagine you're in charge of the census. Each one of your mappers is like a census taker. You give each one a specific neighborhood to cover. That's their little chunk of data. Their only job is to go door to door, count the residents, and then write down the result on a note card in a standard format, like street name, number of residents. That's exactly what a mapper does. It just puts out these standard key-value pairs. Now, after all your little mappers have finished their work, the system automatically takes over for this super important step called the shuffle phase. This is where a lot of the magic happens behind the scenes. The framework goes around and collects all those little note cards from every single census taker, and then it just sorts them into neat piles based on the key, in our case, the street name. So all the cards for Main Street go in one pile, all the cards for Oak Avenue go in another, and so on. And with all our data perfectly sorted into these neat little piles, we're ready for the grand finale, the reduce phase. So now the reduce function comes in. A reducer is like a supervisor. They walk up to one of those piles, let's say the Main Street pile. They take all the cards and they just add up the numbers. That's it. They write down one single final total for that street. That is the reducer's job, to take a key with its list of values and just boil it all down to one final answer. Theory is great, but let's make this real. We're going to walk through the most famous MapReduce example there is, the hello world of big data, word count in action. So the goal is simple. Count up every single word in a giant library of documents. To see how it works, though, we'll just use a tiny input, 2 simple sentences, and we'll pretend each one is being processed on its own separate computer. Okay, let's follow the data flow. In the map phase, each machine takes its sentence, chops it into words, and for every word, it spits out a pair like word 1. So the becomes the 1, quick becomes quick 1, you get it. Then, boom, the shuffle phase kicks in automatically. The system grabs all the pairs with the same word and groups them together. So every the 1 from all the mappers ends up in the same place. And finally, the reduce phase. A reducer takes a group, like the, with its list of ones, 1, 1, and just sums them up to get the final count, the 2. Simple as that. And this right here is the part that should blow your mind. All of that complex, distributed work we just saw, the parallel processing, the shuffling, the sorting, it's all generated by these two ridiculously simple pieces of logic that you write. On the left, that's the mapper logic. For each word, just emit the word and the number 1. And on the right, the reducer. For any given word, just add up all the counts you got. That's it. You write that, and the framework orchestrates this massive, complex dance across thousands of machines. It's incredible.
Now, this simple idea didn't just stay a secret inside Google. No way. It lit a fuse that created the entire big data industry that we know today. Let's look at the revolution it sparked.
The whole thing started with that Google paper in 2004. It was like they dropped a blueprint into the world. Just a year later, the team behind an open-source search project called Nutch said, hey, we can build that. And by 2006, that little project got spun out, got its own name, Apache Hadoop, and just like that, the power of MapReduce was in the hands of developers everywhere. It democratized big data.
So let's quickly recap the key takeaways here. The problem? Data was just getting too darn big for any single computer to handle. The solution? 2 simple functions you write. The map function is your worker bee, breaking down data into key value pairs. The reduce function is your manager, combining all the values for a key into a single result. And its legacy? Well, this whole divide and conquer approach is basically the grandparent of almost all modern big data frameworks.
So now that you've got the blueprint, let me leave you with a little puzzle. Imagine you have a massive data set from an e-commerce site, millions of transactions. Each record has a product ID and a sale amount. How would you design a map function and a reduce function to figure out the total sales revenue for every single product? Think about it, because once you can answer that, you really get the power of the MapReduce paradigm.